about electric potential difference for different cases, and we will see how we calculate the electric potential difference for each. First, let's start with defining the electric potential difference. It is defined as the amount of work done to carry a unit charge from one point to another in an electric field. So if we have an object and we want to move it, we need energy. If we have a charge that will be moved in an electric field, there will be a work done by the electric field, or there will be an energy that is used to move it in this electric field. This energy to move it is the electric potential energy. So work, which is force times displacement, will result in moving this. So in other words, the potential difference is defined as the difference in electric potential of two charged bodies, or between two charged positions. So if we have a charge and we use the formula V equals KQ over R to calculate its electric potential at a position, its electric potential at a different position will be different. And the unit for electric potential difference is the same as the unit of electric potential, which is volts, and it is symbolized by V. Now, the first system, if we have two charged plates, whenever we have a charge, then there is an electric potential. So if we have two charged plates, then each of them has an electric potential. Each plate results in an electric potential. The electric potential difference between the two plates is found using this formula, delta V equals ED, where delta V is the electric potential difference, E is the electric field measured in volts meters, and D is the separation distance between the two charged plates, and D is measured in meters. Now the second case that we have to consider is when a charge moves in an electric field. At each position in the electric field, the electric potential is different. So the electric potential at different positions will not be the same. Then there should be a difference between the two positions where the charge is. So the electric potential difference between two positions in an electric field, or experienced by a charge moving in an electric field, can be found using this formula. Delta V equals minus ED cosine theta, where delta V is the electric potential difference measured in volts, E is the electric field measured in volts meters, D is the magnitude of the displacement in which the particle moves, and cosine theta is the angle between the direction of motion and the electric field. Let's apply. Sample problem 1. Find the electric potential difference between two charged conducting plates separated at 20 millimeters. So let's write the given. We have the separation distance, which is 20 millimeters. We convert it to meters, it becomes 20 times 10 to the power negative 3 meters. Given that the electric field between them is uniform and is of a magnitude of 300 volts per meter, so the electric field is 300 volts per meters. We have to find the electric potential difference, delta V. Okay, we have two charged conducting plates. Then, to find the electric potential difference, we use the formula delta V equals ED. We replace E is 300 and D is 2 times 10 to the power negative 3. We get the answer for delta V as 0.6 volts. Sample problem 2. Consider two conducting charged plates separated at 0.4 centimeters. So given is the separation distance between them as 0.4 centimeters. The electric potential difference between the plates is 12 volts. Delta V is 12 volts. Find the magnitude of the electric field. So we have delta V and D. We have to find E. Do not forget to convert the distance. It should be in meters. So from centimeters to meters is times 10 to the power of negative 2. Those are the plates, and this is the separation distance between them. We use the same formula, delta V equals ED. We divide both sides by D to obtain E. Then E equals delta V over D. we replace delta V is 12 volts, D is 0.4 times 10 to the power of negative 2 meters, and we get the answer for E as 3000 volts per meters. Also remember that the electric field always points out of positive into negative, so this is the direction of the field if we wanted to draw it. Sample problem 3. An electron is released from rest in a 1000 volt per meter east electric field. So we have the electron, we know its charge is negative 1.6 times 10 to the power of negative 19 coulombs. Released from rest, it means that its initial velocity was 0. We will see if we need this. In a 1000 volt per meter east electric field, and the electron moves at a distance of 20 centimeters. So we have the electric field is 1000 volts per meters, and the separation distance is 20 centimeters. We convert it to meters. Find the electric potential difference experienced by the electron. We have to find delta V. So the electric field points east. This is the electric field. If the electric field is pointing this way, then what causes this field? It's either a positive charge and the electric field diverges out of the charge, or a negative charge and the electric field converges into this negative source charge. So it's one of the two possibilities, either out of positive or into negative. In both cases, it points east. Okay. When we release an electron in this field, the electron will be repelled away from negative if it was a negative source charge, or attracted to the positive source charge if it was the one that causes the field. In both cases, the electron will move this way. So, as you see, the direction of motion of the electron, let's repeat, the direction of motion of the electron was opposite to the electric field or against the electric field, which is an angle of 180 degrees. So we apply the formula delta V equals minus ED cosine theta. We replace E is 1000, D is 20 times 10 to the power of negative 2 after being converted to meters, cosine theta, which is cosine 180. And the answer is 200 volts, positive 200 volts. Let's see, does this make sense? Okay, the electron moved from negative to positive, or from low potential to high potential. So the difference in potential should be positive. So yes, it makes sense. This is correct. Sample problem 4. Now a proton is released from rest in a 500 volts per meters west electric field. The proton moves a distance of 20 centimeters. Find the electric potential difference experienced by the proton. So we have the charge of the proton plus 1.6 10 to the power negative 19 coulombs. The distance is 20 centimeters. We convert to meters. The electric field is 500 volts per meters, and find the electric potential difference delta V. Since the electric field points west, then it points this way. Again, it is a result of a positive charge or a negative charge in this case. So if we release a proton in this electric field, it will be either repelled by the positive source or attracted to the negative source. In both cases, it will move this way. So its motion was the same as the direction of the field. Then the angle between the direction of motion and the electric field is 0 degrees. We apply the formula delta V equals minus ED cosine theta. We replace E is 500, D is 20 times 10 to the power negative 2, and the angle is, in this case, is 0 degrees, and we get the answer as negative 100 volts. Let's validate. Okay, the proton moved from an area of high potential to an area of low potential, from positive to negative. So the difference in electric potential should be negative. Yes, this answer is valid. Sample problem 5. A 2 microcoulomb charged particle is released from rest in a 240 volts per meters north electric field. calculate the particle moves a distance of 10 centimeters, find the electric potential difference experienced. So the charge is 2.4 microcoulombs, the distance is 10 centimeters, and the electric field is 240, find delta V. Okay, so the electric field points north. It will be either a result of a positive source charge and it diverges out, or a negative source charge and it converges in. If we place this 2 microcoulomb charge is positive, if we place it in the field, it will move away from positive and towards negative. So it's moving in the same direction as the electric field, then the angle is 0 degrees. We apply the formula delta V equals minus ED cosine theta, then delta V equals minus into 240, 10 times 10 power negative 2 cosine 0, and we get the answer as negative 24 volts. Okay, so is it valid? Yes, actually the particle moved from high potential to low potential, so the electric potential difference should be negative.